When we first introduced the term EMF, I told you that we would see some cases where voltage developed some problems, and now we're going to look at one of those. Now, as we discussed earlier, if we are in electrostatics, if we're just looking at charges sitting around, we notice something interesting about the character of the vector field. Remember that a vector field is just something that has magnitude and direction everywhere. So wind, for example, if we could put a little marker everywhere in the air, that would tell us the direction and the speed of the wind, that would be a vector field. Temperature, on the other hand, would be a scalar field. We could measure the temperature at every point in some region, but it wouldn't have a direction associated with it. So, for a vector field like we get from just an assortment of charges, what we find is it's irrotational. What that means is the lines leave some points, positive charges, and they terminate on other points, negative charges, but they don't form loops. If we were instead looking at the velocity field of bathwater going down the drain, that is not irrotational. It does form a loop as it circles around the drain. When you get to vector calc, you'll say that irrotational fields like this have zero curl, and you'll write it with this directional derivative we've talked about. What looks like the cross product of that and the vector field equals 0, that means it's irrotational. And that also means, it means a few things. It also means the field is conservative, which means it's path independent, and that means we can define a scalar field that we call the potential. In our case, we called it the electrostatic potential, or the voltage. So one of the ways we can represent this is we can say the line integral around a closed loop of E dot dl equals 0 in this case. Now, if we move a charge around a closed loop in this electric field, that tells us we do no work. And another way to state that would be Kirchhoff's loop rule. As we go around a loop, the sum of the potential jumps and drops, which would be E dot dl, because that gives us a voltage, is 0. The problem is Kirchhoff's law isn't really a law. The actual law is Faraday's law, and it says this. Now, of course, if we don't have any magnetic flux going on, like we didn't when we were looking at those simple circuits, this was 0, and we're back to being okay with Kirchhoff's voltage law. Now, we don't have path independence if there's a changing magnetic flux. In vector calc, we'd write that as curl of E is not equal to 0. That means we can't define a potential. If we want to look at this in action, we can look at our generator above. If we just have the loop of wire here sitting there, of course there's no potential difference. All of that conductor is at the same potential, no current flows. But when we start turning it in the magnetic field, we actually get a electromotive force and charges do move. Now, this is such an important and overlooked fact that I wanted to direct you to this video online. This guy is Walter Lewin. He used to be a professor at MIT, and he's got a whole series of lectures, Intro Physics 1 and 2. And if you look at this particular YouTube video, or you can Google Lewin and Faraday's law, and you'll find the same lecture. He's got a very simple circuit drawn here. All we have are two resistors, 1 and 2, and a voltmeter connected at these points D and A across them. This would be completely dull. We'd get 0 for the voltage at all times, except that in the center he's got a solenoid sticking out of the board, and it has the magnetic field is also coming out of the board, and it's increasing. Now, what's the circuit's response to this? If out of the board flux is increasing, point your thumb into the board to counteract it, and your fingers will curl in the direction of these little purple arrows. Now, if instead of this we put a battery here somewhere instead of the solenoid, we would get the same voltage across each resistor. They're in parallel in that sense, and we know we get the same voltage across each. Now, since there's not a battery, but instead this solenoid with the changing B field, we're going to see something very different. So we have this EMF coming from d phi dt. Now, of course, we could specify the magnetic field and the area and how fast it changes and all that and come up with whatever EMF we want. And he just said, let's say we do that and get 1 volt for our EMF. Now, we can say the resistors are in parallel here, but since they're the only two things, they're also in series. And the 1 volt going through here, we've got 100 ohms plus 900 ohms, that's 1,000 ohms. So 1 volt through 1,000 ohms gives us 1 milliamp of current. What's the potential difference across R2 here? Well, it's pretty simple. VD minus VA should be IR2, which is 0.9 volts. Now, what about the other side? We again want to measure VD minus VA, but we're going to get a different answer. When we do that, we get our 1 milliohm, 100 ohms, we get negative 0.1 volts. We get a different answer here than here. And remember, the voltmeters, these are just tacked on. This is the only real part of the circuit, right? The important part. And the voltmeters are connected in the same places. So this voltmeter has leads here, and this voltmeter has leads there, and they give us different answers. This is completely crazy. Now, he does this demo with oscilloscopes where he shows you this. He turns on the solenoid and you can see this happen. And again, the reason it happens is we don't have path independence anymore. It matters which way you go. He said he has had physics professors and electrical engineering professors, and remember, this is at MIT, so they're not likely to be idiots, accuse him of trying to trick the audience with this because they have not kept the fact that the E field is now path dependent in their minds. They think there's something else going on. He also shows you, when he turns the solenoid on, he shows you what the oscilloscopes display. And if you look, they're obviously completely different pictures. They're connected at the same place, but they're measuring different things because of this lack of path independence. Now, one of the other things associated with Faraday's law is eddy currents. This is not somebody's name, but eddy like a circular motion in water. Anywhere the water's velocity field has non-zero curl, like a whirlpool, that's where there's an eddy current. When a conductor is moving through a magnetic field, eddy currents are set up and they act like velocity-dependent friction. Air resistance is a velocity-dependent friction. There's a neat demo I usually do where I take a, say, 1 meter long copper pipe and drop a magnet through it. If I just dropped, say, a rock through it, it would fall through in half a second, but the magnet takes more like 30 seconds to fall. Why does that happen? Well, let's say we drop the magnet North Pole first, and this darker one is our real magnet. As it falls, we're introducing a downward directed flux into the copper tube here, and it responds by giving us an upward directed flux, which acts like a North Pole here. So it's like I've got this phantom magnet here underneath it, and it's pushing back on the real magnet. If I look at the other end, as it falls, the down the page flux or field is disappearing, and the copper pipe above it tries to keep that alive by manufacturing what is essentially a North Pole right there. So that north is pulling on that south. So this magnet is being pushed from the bottom and pulled from the back, and that's why it's so slow. This eddy current braking is used in a lot of different things. It's used in slowing down roller coaster carts, high-speed trains, in an exercise bike when you want some artificial resistance there to build up your muscles. That's a common way to get it. So this is all over the place. It's in scales in the chem lab. Now, we saw earlier that the same device could be a motor or a generator, and this is why electric cars that have motors at each wheel, you also use them for braking. They're able to recapture some of that energy and charge the batteries. That's partly why they're so efficient. What you might be surprised to learn is it's not just the same device acts as a motor or a generator depending on how it's operated, but a motor is also acting as a generator at the same time. So the EMF that the motor produces in this configuration is called back EMF, since it's fighting the EMF that's actually driving the mower. If you know about this, that'll explain a few things you may be familiar with. Now, to look at those, let's consider a motor to just be a coil of wire. It's not much more complicated than that. It's basically a coil of wire in a magnetic field. If we say it has some resistance R, we could say, all right, if we have an external source of voltage V, we should get a current V over R. That's simple enough. But back EMF works the other way, and that reduces the current from V over R to V minus epsilon over R. We know for a generator what epsilon equals. It's NBA omega sine omega t. Once the motor is at operating speed, if it's not being loaded by something, so we got a power drill and we're just spinning it in the air instead of trying to drill through steel or something, all it has to do is overcome its own friction, and it'll spin so fast that E will just be a little bit smaller than V. So let's put in some numbers. Let's say at no load, we connect it to a 120 volt wall outlet and the back EMF is 110 volts. If R for the drill is about 5 ohms, and this is pretty typical, our full speed current would be 120 minus 110 over 5, or 2 amps. Now when the motor starts initially, it's not moving. Omega is 0, so back EMF is 0. Our current then is 120 minus 0 over 5, or 24 amps. This is huge. This is a giant current compared to when it's running. You may have noticed that if a large motor like your air conditioner or vacuum cleaner turns on, the lights dim momentarily, and then they come back to normal after the motor gets up to speed. This is because of what's called the inrush current or the startup current, the surge current. You see it printed on motor nameplates sometimes as LRA, which is locked rotor amps. All of that says how much current will this use when you first turn it on. Now, if your circuit breakers tripped instantly as soon as you went above their nameplate value at all, you'd have to have much larger breakers in your house anywhere you were going to use a motor. They don't work this way, fortunately, and if you're just a little bit above the rated value, it can take minutes to an hour or more to trip. The farther you are above that rated current, the faster they trip. This also explains one of the ways you can kill a motor. We already know if we want a high torque motor, if we want it to be able to do a lot of work for us, we need lots of loops of wire. So that's a high value of N. And there's 2 ways to do this. First, we don't use, this on the left is ordinary wire like in your house. You notice there's a thick plastic layer over it. On the right, we have what's called magnet wire, not because it's magnetic, because it's not. It's just thin wire that's been coated with shellac, kind of like paint, instead of a thick layer of plastic. The reason is this lets us put more turns of wire where the B field is. So thin wire is what we want. Also, the thinner the wire is, the more of it we can put in there. So not only are we getting rid of the insulation, we're making the wire itself smaller. Now let's go back to using the drill, and let's say you're trying to drill through something very tough, or the drill binds up and starts to slow down. When it slows down, omega drops. When omega drops, the back EMF drops. That means the current and the power it uses is increasing. So you don't pay any attention to that. You keep squeezing the trigger. It's almost completely stopped. Once it gets almost completely stopped, we know that the current is going to be in the ballpark of 24 amps. Only instead of that happening for just a second, it's going to be going for several seconds while you grind this thing to a stop. That very high current means very high heat buildup. I squared R is going to be huge, and you can burn through this painted on layer of insulation very quickly, and now you've got a short circuit and you need a new drill.